Alright, so this is our study of rotational statics from class the other day. Just worked several problems, and so I'm going to walk you through some of those. First, just a reminder of the definition of torque that you explored through your activity, where you placed the differing weights at different distances from the fulcrum and found that when it was not rotating or changing its rotation, the angular velocity or the angular acceleration was zero because those torques were balanced. Not necessarily the mass is balanced, not necessarily the forces, but the torque, which is the R cross F, or the position vector cross the force vector, for each of those in the respective directions were balanced. And of course a reminder that when we multiply R cross F, that is a vector product, which the direction is perpendicular to both R and F, and the direction is defined by the right-hand rule, and the unit is Newton meters, and we'll be reminded later again that that's not to be confused with joules, which is a Newton times a meter, which is a dot product, because this is a cross product where the two components are perpendicular rather than parallel. So if we look at an example where we have this meter stick, or the stick that's balanced at a point P, and the meter stick has a mass of 100 grams, which translates into 1 Newton, and it's off center. The fulcrum is 0.15 meters away from the center, and then we've hung this extra 50 gram mass an additional distance away. And so the question is, where would you place a 200 gram mass on the left side of the meter stick to balance both the meter stick and this extra 50 gram mass? And then we had this rod of 2 meters long and with a mass of 4 kilograms, and asked ourselves what force, what tension would be necessary pulling up at 1/4 of the length from the right end in order to balance the meter stick if the fulcrum was 1/4 of the length from the left end. And so of course first we have to pick our point of reference, and we're going to choose the fulcrum because there is a normal force acting on the meter stick at the fulcrum, and we want to be able to ignore that. And so if we pick a reference point P, then that means that the torque due to that normal force at point P is 0. And so we can eliminate one of the unknown forces that we don't really need. And so then with point P being our reference point, we can look at the meter stick itself is exerting a torque in what I'm going to call the negative direction, as indicated by my convention here. It's clockwise, and so if I call that negative, it has a mass of 4 kilograms resulting in a weight of 40 newtons, acting a distance 0.5 meters from the reference point P. Therefore, that negative torque, as indicated by the green color, is 0.5 times 40. And of course, the R vector and the F vector are at right angles to each other, and so it's sine of 90, which is 1. And so that's the negative vector. And so what positive vector, or due to the blue tension force, is necessary to balance that? Well, the tension force is a distance 1 meter away from point P, so the R vector is 1. I'm looking for T, so I'll call that T, and then of course the angle between pulling straight up and the lever arm is 90, and sine of 90 therefore is 1. And so I know it's not accelerating, and so therefore the torques are balanced. So the net torque is 0, and then it just becomes a matter of algebra, giving me that 20 newtons. And this is just showing that I can find that normal force two different ways. One is I can use an F net statement in the y direction. If I assign up as positive, then there's the normal force up on the rod, there's the tension force up on the rod, and the mg force down. So the net force equals N plus T minus mg. But since it's not accelerating, the net force is 0, and so I can solve for n that way. And then the other method I can use is I can choose a net torque statement. I just have to pick a point different than point P, because if I choose point P, then there's no torque due to the normal force, and so I can't find it. But if I pick the end of the rod, as indicated by the letter E in this diagram, then I can do a net torque statement. It's not rotating relative to point E, and so the net torque relative to point E is 0. And you can see there that I've then designated the 3 different forces that are exerting torques relative to point E. And since the normal one was the only one I didn't know, I could solve for it that way. The work that you see is just me proving my answer that I got from the net force statement using a net torque statement. Next example, we have a meter stick that's suspended from a rope that's hanging 10 centimeters from its center. And so you can imagine that left to its own devices, the meter stick would fall down and rotate clockwise in this frame of reference. But it's also got 2 other masses hanging on it. There's a 6 kilogram mass hanging 5 centimeters from the left end, and a 2 kilogram mass hanging 10 centimeters from the right end. And I get to place an additional tension force, call it T2, equal to 20 newtons. And the question is, where can or should I place it? Well, again, the first thing I'm going to do is I'm going to choose a point of reference, and I can't pick where T is connected. I can pick where T1 is connected because I don't know where T2 is going to go. And so that's an ideal reference point, is point P where T1 is connected. And so therefore there is a red vector due to the meter stick's mass itself of 0.92 newtons, acting 0.1 meter from the reference point. There's a blue vector also in the positive direction, 20 newtons, 0.5 away from the reference point. There's an additional negative torque provided by the 60 Newton force 0.35 from the reference point. And then all of those are being balanced by this 20 Newton force that I'm going to call placed R distance away from point P. Of course, if it's balanced, then the net torque is 0, and so now it's just a matter of using algebra to solve for R. And notice that I get R is 55. Now, the value of R is positive 55, and I didn't designate which direction T2 should be pulling. It can either be pulling up or down. And so if you look at the placement of my reference point P, I just need something that's going to result in a positive torque. In other words, a clockwise torque in this frame of reference. And because the 21, which is in the negative direction, is larger than the 10.092 in the positive direction, and so I need more additional positive torque. One way to do that would be to pull down to the right of point P. The other option would be to pull up to the left of point P. Both of those would result in positive torques, or torques in the clockwise direction. As you can see, I don't have enough meter stick to the left. I only have 40 centimeters to the left of point P, and so there's not enough meter stick to pull up on the left side, but I can indeed pull down 55 centimeters to the right of point P to balance this. All right, one more. If we've got a rod, a firm rod that's attached to the left end of this plank that's suspended from the ceiling, we'll say, and it has a mass of 2 kilograms, and there's another force T that's pulling up 0.3 meters away from the rod. What force T is necessary to keep it from rotating? Well, I'm going to pick a point of reference P. Since I don't know the force of the rod, I'm going to choose that point so that I can ignore the force due to the rod, and I can designate that there's an mg force acting 1 meter away from that reference point, and it has a magnitude of 20 newtons. And so, excuse me, not 1 meter, 0.95, because it's 5 centimeters from the end, and the center is 1 meter from the end. And so then that's balanced by a negative torque acting 0.3 meters away. I can solve for T since they're balanced, and that gives me a tension of 63 newtons. And then, of course, the follow-up question would be now find FR. And as we saw in the previous example, I can do that two ways. I can do an F net statement where there's T up, FR either up or down, and mg, which is clearly down. And there's no net force, and so I can set that equal to 0, solve for FR, and you'll notice that I get a negative number for FR if I've chosen up to be the positive direction. Well, that's no problem. It just means that the rod then must be pushing down in order to keep the rod from accelerating up. And so, again, if you don't know whether something's acting up or down, just call it positive, move forward, and then if you're right, if it was in the positive direction, then you'll get a positive answer. If you get a negative direction, or a negative answer, that just means it's in the opposite direction. All right, so now we've got a 20 kilogram seesaw that is 5 meters long, and we've got a young man who weighs or has a mass of 100 kilograms, and he's going to try and seesaw by himself. And so he slides the center of the seesaw over to where there's only 1.5 meter on his side, and there's the remaining 3.5 on the empty side. And so the question is, can this kid balance the empty seesaw alone? And if so, where does he need to sit? Well, there's only the 3 forces acting on the seesaw, and 2 of them are unknown. One of them, or excuse me, one of the forces is known, but I don't know where he's going to sit, and so the torque is unknown. But if I pick the reference point of the fulcrum, then the normal force on the seesaw can be ignored. And so that's what I'm going to do. I'm going to pick the reference point at the fulcrum. Therefore, the weight of the seesaw, 200 newtons, is acting 1 meter away from there. And I can then place him at a distance r with his 1,000 Newton force and solve for the balanced forces, the balanced torque. And that gives me a distance of 0.2 meters. And so he only needs to sit 0.2 meters from the fulcrum in order to balance the empty side of the seesaw. But then that's not fun. You know, he doesn't want to just be alone, and so he calls his little sister over, and they both sit at the opposite ends of the seesaw. He sits then 1.5 meters away from the fulcrum, and she will be 3.5 meters away. And the question is, what's the minimum mass of his little sister for them to be able to balance and play on the seesaw together? And of course, that was the homework assignment that I gave. All right, another example. If I hang a meter stick of mass 88 grams, 0.25, suspended by a string 0.25 meters away from the left end, and hang a 1 kilogram mass 5 centimeters from the right end, where should I place a 30 Newton force in order to balance it? Well, of course, again, the rope that's hanging from the ceiling is unknown, and so I should pick that as my reference point so I can ignore the torque due to it. I get positive direction as clockwise. The green vector then, which is the meter stick's mass itself, or the weight itself, produces a torque that is at a reference position vector 0.25 and a magnitude 0.88 newtons. And then there's a orange vector that is the 1 kilogram mass, which is 10 newtons, acting 0.7 away from the reference point. And then again, I get to place my 30 Newton force wherever I want. I don't know if it's going to be pulling up or pulling down, positive or negative, and so I'm just going to assume it's positive and see what happens. I get a 30 Newton force at a distance r, and then set those equal to 0 because all those torques are balanced. Those numbers below are just doing the math that 0.25 times 0.88 is 0.22, and 0.7 times 10 is 7. Combining those, I get 7.22 plus 30r equals 0, and therefore r must equal negative 0.24 meters. So again, I can either pull down on the left side 0.24 meters away, which will provide a negative torque with this frame of reference, or I can pull up to the right side 0.24 meters away from the reference point. Both will result in balancing out these torques. And so this is just like the previous problem we worked, where I have a rod pushing down and a tension pulling up, an extra mass on the end and the mass of the rod, or the bar itself, and you can solve for the tension. And then, of course, after solving for the tension, you can use either an F net statement or choose a different reference point and use a net torque statement to find the force of the rod acting on the bar. And again, of course, it's pushing down. Because of the huge tension force necessary to keep this thing from rotating, the bar must be pushing down to keep the whole thing from translating up.